Hello everyone, welcome back to series of solid state. So this is a solid state part 5. In the previous 4 videos, we talked various parts of a solid state like crystalline solids and amorphous solids, and the different types of crystalline solids we discussed, and also what do we call basic crystal systems, how basic crystal systems are further divided into Bravais lattices, and what are the unit cell parameters, and what are the different types of unit cells present in what do we call cubic unit cells, like simple cubic, face centered cubic, body centered cubic. And also we calculated what do we call effective number, that is also known as the rank of the unit cell. And now we have to study the internal structure of these cubic unit cells. Internal structure of cubic unit cells means we have to find, so in case of simple cubic unit cell, what is the packing efficiency, and also here what is the relation between edge length and atomic radius, and also we have to calculate the density of that unit cell, and various parameters we have to identify, we have to calculate coordination number, we have to calculate. And before going to that calculation part, first let us take the definitions of various parameters. So without making any delay, let us get into the video number 5. So here the important parameters. First, let us try to understand the definitions of various parameters. Let us try to understand the definitions. So here some important terms related to cubic unit cells. Some important terms related to cubic unit cells. And in this, the first one we have to talk about Z effective. The first one we have to talk about, that is Z effective. So already we have calculated Z effective of various cubic unit cells, and what is the exact definition of Z effective, and also based on Z effective, what are the important parameters we can develop. Let us take here the first one, that is Z effective, that is effective number of atoms present in a given unit cell. Already we have calculated simple cube has 1, body centered cube has a 2, face centered cube has a 4. And the next one, that is the atomic radius. Atomic radius, so the exact definition, if you see, it is half the distance between the nuclei of two nearest neighbors in a crystal. So here half the distance between the nuclei of two nearest neighbors in a crystal. For example, here we have two atoms like this, two atoms, these two atoms are in contact, and if you take the distance between the nuclei of these two, distance between the nuclei of these two, in that half the value, that is called the radius of the atom. And how to calculate radius of atom? These two atoms are in contact, and you have to take the distance between the nuclei of these two atoms, and half the distance if you take that is called atomic radius. That is the definition of atomic radius. And the next one, coordination number. Coordination number, it is the number of nearest neighbors. It is the number of nearest neighbors, how many nearest neighbors are present, so how many nearest neighbors are possible. And that number is called, what do we call, a coordination number. And we have to calculate all these parameters for three types of cubic unit cells. And the most important one, that is packing fraction. And in fact we have to calculate the packing fraction of all atomic solids. Even we have to calculate the same for all ionic solids also. See, what is the exact meaning of packing fraction, packing efficiency? Very simple thing. Here we have a unit cell, cubic unit cell we have. What is the total volume of this unit cell we have to find? And in that, how many atoms are present we have to find? And what is the exact volume occupied by those atoms? Of course, the available volume is volume of unit cell. This is total available volume, but definitely the total volume is not occupied by atoms. In between, there are some empty spaces. Those empty spaces are called voids, and we need to find how many atoms are present effectively, and what is the volume of each atom. If you know all these things, we can easily find the packing fraction. So it is the ratio of effective volume occupied by the atoms to the volume of unit cell. So this is the available volume. In this, what is the exact volume occupied by atoms in that unit cell? If you calculate the ratio of these two, that is called packing fraction. And effectively, how many atoms and the volume of each atom? This is the total volume of all atoms in that unit cell, and this is the volume of unit cell. This ratio is packing fraction, and if you want packing efficiency, that should be multiplied by 100. And the next one, I told you, along with that cubic unit cell, we also have hexagonal unit cells. We will also discuss that hexagonal unit cell. But first, since we are discussing cubic unit cell, it may be simple cube, face-centered cube, or body-centered cube. So volume of the unit cell is a cube. Volume of cube. Volume of cube, where A is the length of the edge. You already know. So all edge lengths are same. And here, volume of that particular unit cell, cubic unit cell, any kind of cubic unit cell you take, and its volume is A cube. And one more important term, we have to take a phase diagonal. So what is the exact meaning of phase diagonal of a cubic unit cell, and what is its value? If we can calculate these things once, because in the coming videos, frequently we are talking about we'll be talking about a phase diagonal, body diagonal, relation between phase diagonal and radius of atom. See, for example, if you take one face of cubic unit cell, this is one face. And here the exact definition of a phase diagonal, if you see, so this is the distance between the two opposite corners of a face. Distance between two opposite corners of a face is called phase diagonal. We are interested in finding this particular value, and we know, so here this is edge length, this is also edge length, and edge length, that is A, this is A, and according to the Pythagoras theorem, so AC here, this is a phase diagonal in triangle ABC, so that AC square is equal to phase diagonal square is equal to edge length square plus edge length square. AC square is equal to AB square plus BC square. In place of AC, in fact, that is our phase diagonal, and AB, value of AB is A, value of BC is also A, and this is equal to 2A square. And in fact, we need phase diagonal, that is that is equal to root 2 times of A. And whatever it may be the unit cell, like it may be a simple cubic unit cell, face centered cubic unit cell, body centered cubic unit cell, whatever it may be the type of unit cell, phase diagonal value is same, that is equal to root 2a. In the future videos also, wherever we need phase diagonal, straight away I'll be taking root 2a, and this is the what we call a proof for the value of a phase diagonal. Now, what is the exact meaning? Already told you, it is the distance between two opposite corners of a face. And in fact, there are 6 faces. You already know cubic unit cell has 6 faces, and each face has 2 phase diagonal. Altogether, how many phase diagonals are present in a cubic unit cell? Obviously, it is 12, and the value of a phase diagonal is root 2a. Root 2 times of a are 1.414a. So here this is about a phase diagonal. Now, let us take one more term, that is body diagonal. First, let us take the exact meaning of body diagonal. How many body diagonals are present? What is the value of body diagonal? Because in all calculations, totally many times in all calculations, we'll be getting phase diagonal and body diagonal values so many times. So once let us understand the definition and value, and indirectly we can use the standard result wherever it is needed. See, for example, this face, back face, this face I'm taking back face, and this face I'm taking front face. So here this is a back face, this one I'm taking. So this is a back face, and another face we are taking, that is a front face. So here let me try to give a different color. So here the front face is like this. So this is the front face. Earlier, in case of a phase diagonal, we took two opposite corners of a what do we call a one face. But now we are taking two opposite corners of opposite faces. So these two faces are opposite faces, and this is the top corner and this is the bottom corner, and this distance The distance between two opposite corners of opposite faces is called what we call a body diagonal. And again, here we have a triangle, and this is a triangle ABC. And if you carefully observe, this AC is body diagonal, BC is edge length, and this is face diagonal. Just now we have calculated, which is equal to root 2 times of A. Again, from the triangle ABC, we can write AC square is equal to, in fact, AC is body diagonal here, and that is equal to AB square plus BC square. AB value is root 2A. Just now we have calculated. BC is edge length, and we know the result. And ultimately, if you simplify, you will be getting body diagonal of a cubic unit cell is root 3 times of A. Cubic unit cell, I am saying, it may be a simple cube or face-centered cube or body-centered cube, irrespective of nature of unit cell. For all cubic unit cells, undoubtedly you can take a body diagonal value is root 3 times of A, whereas face diagonal value is root 2 times of A. And here, how many such body diagonals are possible means it is connecting two opposite corners of opposite faces. Totally, like that, we can draw 4 body diagonals. Like that, here, this is one body diagonal, and if you take like this is one body diagonal, and from this corner you can move like this is one body diagonal, and from this corner you can move. Altogether you can create how many? 4 body diagonals. That is the definition. It is the distance between two opposite corners of two opposite faces, and of course there are 4 body diagonals, and the value of body diagonal is root 3A. And here, in fact, this standard result we need to remember, right? And these are all the basics we need to understand the internal structure. But in this video, I will try to complete simple cubic structures. The same thing we'll do for body-centered cubic unit cells and also face-centered cubic unit cells. And in fact, voids will also be developed in the next video. But here, let us take simple cubic structures. Let us study simple cubic structures. So in simple cubic lattice, the atoms are located only at the corners. Of course, we know that. And the very important point, according to X-ray diffraction studies, in case of simple cubic unit cell, the particles which are present at the corners of one edge, are in contact. You can see these 2 particles are in contact. But the particles which are present along face diagonal, they are not in contact. You can see some empty space here. This is some empty space. So what is the important point you need to remember? If you can remember this particular point, remaining everything can be derived spontaneously instead of remembering. If you see atoms contact view, in case of simple cubic structure, straight away we can say the atoms which are present at the corners of an edge, they are in contact. That is the only information you need to remember. And by taking this, let us develop. And from this diagram only I'm saying, you can see from this diagram, this is what edge length, this is edge length, and from this point to this point radius, from this point to this point radius. So obviously edge length of simple cubic unit cell, edge length of simple cubic unit cell is equal to 2r, edge length. Now we need to find the volume of this cubic unit cell. Already I told you, it may be simple cube, face-centered cube, body-centered cube. Volume of unit cell is AQ. Volume of unit cell is AQ. And here A is equal to 2R. In place of A, I am substituting 2R. As a result, the volume of simple cubic unit cell is 8R cube. And effective number of atoms, Z effective, already in the previous video we calculated, there are 8 particles at the corners, and from each corner we are getting 1 by 8. 8 1 by 8 means obviously, even though there are 8 particles in total, but from each corner it is contributing only 1 by 8. So totally 8 1 by 8 means effectively there is only 1 atom. And the volume of that atom, effective volume of the atoms, there is only 1 atom. Obviously this is a 4 by 3 pi r cube. And already we discussed what is the meaning of packing efficiency or packing fraction. So packing efficiency or packing fraction, if you take, so this is the effective volume of all atoms by volume of unit cell. Effective volume of all atoms, that is only 4 by 3 pi r cube. And here volume of unit cell is 8 r cube. And if you simplify this, we are finding packing efficiency. And if you simplify this, you will be getting 52.4 percentage. And if it is asked in the examination, you can derive. If you can remember standard result, that is up to you. But it is not memory based. You can spontaneously derive whatever the equation you need. But the only information you need to remember as far as simple cubic unit cells is concerned, that is the particles, the corner particles which are present on one edge are in contact, and these two are not in contact, and this one and this one are obviously not in contact. Only the corner particles of one edge, and percentage of voids will be obviously, that is a 47 percentage, and coordination number. Finally, we need to find the coordination number. Already the definition we have taken, the number of nearest neighbors. The number of nearest neighbors. See, for example, this is one unit cell, this is second unit cell, this is third unit cell, this is fourth unit cell. To define coordination number, we are taking these 4, 1, 2, 3, 4 unit cells. Now, you see, this is the particle sitting at one corner. And already I told you, the particles which are present on one edge are in contact. So this is nearest neighbor. It is present at what distance? A. This is also at a distance A. This is also at a distance A, distance A, distance A, and a distance A. And obviously, this is directly in contact with the what do we call 1, 2, 3, 4, 5. So here you can see 1, 2, 1, 2, 3, 4, 5, 6. So the coordination number is 6. The coordination number is 6. Not only this atom, even if you extend the structure, this atom will be having 6 neighbors. This atom is also having 6. Every atom will be having 6 neighbors. So the number of nearest neighbors is coordination number. Once again, the nearest neighbor distance. The nearest neighbor distance is A. But after completion of the basics, we will also talk about the second nearest neighbor, third nearest neighbor. But if the structure is known, whatever it may be, we can easily calculate. And this is about coordination number. And let us end this simple cubic unit cell finally with the layer structure we have to take. So this is the simple unit cell view. So the particles are present like this. But atoms contact view, if you take, so here totally the particles are present only at the corners, and the particles, the corner particles of one edge are in contact. And here, this is what do we call, if you see from one face, from one side, if you see, the structure will be like this. That means, so here the particles which are lying, these particles are in fact what do we call in eclipsed fashion. Eclipsed fashion. So that means exactly backside there are 4 more particles, and this is the first layer. You can see this is the first layer, and the second layer particles are lying exactly above the particles of the first layer. But definitely this is not in staggered manner, it is in eclipsed manner only. And one more layer if you take, or sequence of series of layer if you take, so here whatever it may be, you can assume however it may be. So these are the various layers. For example, so this is first layer you take, this is second layer you take, third layer, fourth layer, 4 layers of atoms we have taken. And if you are talking about one unit cell, so here this is the unit cell like this, these 8 atoms. So altogether, so here that is said to be one unit cell. And here how to see the coordination number? You just see one atom here. So here one atom, if you see, this atom if you see, this is directly in contact with the 1, 2, 3, 4 atoms of same layer, 4 atoms of same layer, and behind this one more atom is present. In fact, here you can see this is what we call a 5th atom, but that atom belongs to the next layer, and top of it there is one more layer. Top of it there is one more layer, there one particle, and here the coordination number is 6. So this is about layer side view, and coordination number is 6. And these kind of things we need to discuss for what we call face centered cubic unit cell and also body centered cubic unit cell. But that will be done in the next video. Thank you very much.